So in production engineering, we typically need fluid properties, or what we call the PVT properties, for our calculations. For the case of production engineering, for example, one very typical application is to calculate pressure drop in multi-phase flow, or also single phase oil or gas. So then we have, let's assume we have a part of the tubing, and then we have two phase or three phases. Let's say we have three phases. Let's say we have the gas, and then we have oil, and then we might have water, a little bit of water in the oil. And let's say that we are here at some conditions of pressure and temperature, and we want to know what we are the fluid properties. So some typical fluid properties we need, they are of course for each phase, oil, gas, and water. And we need, for example, the density is very important for example, pressure drop calculation. Then we have the viscosity is also important, also for pressure drop. We need also sometimes interfacial tension. There are some pressure drop models that require interfacial tension, for example, of oil and gas, water and gas, and oil and water. We might need also the enthalpies. Okay, so the enthalpies might be the enthalpy of the oil, enthalpy of the gas, and enthalpy of the water. This is important for temperature calculations. But we also need something to tell us how much there is of each phase. Okay, so we need, if we say, well, what we need really is the mass flow of oil, mass flow of gas, and mass flow of water. With these mass flows I can get, and the densities, I can get, well, the Q of oil, the Q of gas, and Q of water. And with these ones, I can get the superficial velocities of oil, superficial velocities of gas, and superficial velocities of water. And then ultimately, with all of this information, I should be able to get this famous dP, dx, or also my dt, dx along the pipe. So there are a bit different approaches. How do I calculate this part? And we will see it depends a bit on the fluid model that I'm using. So essentially there are two approaches. Okay, one of them is compositional, in which I need a composition set I. Remember, set I means is the mole fraction. You have different components, C1, C2, C3, and here I have the mole fraction, whatever the well is producing. Okay, then I need to have an equation of state that I'm going to use. For example, this can be Penck-Robinson. It's an equation that is typically used in petroleum engineering, and I need also to have some US parameters. Okay, that for example, you need to know how you're going to combine the properties of all the different components. You need, for example, the mixing rules. Okay, then you also need, for example, the binary interaction parameters. Okay, and typically, of course, well, we don't typically work with always tabulated components, but we also have some pseudo components that we need to provide the properties for. So here we have some pseudo components. Okay, so that's the way, and when I have that, well, I can actually generate all of these. Okay, I can generate all of that. And how do I find these typically? Well, from this compositional model, I can also generate, typically is the mass fraction, okay, of oil, gas, and water. Okay, it could be that the mass fraction is going to be, for example, XO is going to be the mass flow of oil divided by oil plus gas, okay, and then the gas will be, if we have, let's say, only oil and gas, okay, and then to calculate the mass of oil, you're going to take the total, and then you're going to multiply times this XO, okay, and the same thing for the gas. Okay, so this can be an approach. Okay, the only thing is that this approach is sometimes very expensive to run it live. So to be running at every point in the tubing where I have some pressure and temperature, then I have to trigger an equation of state calculation that typically involves first is an equilibrium calculation, a flash calculation, what is called, to find out if I'm in a mixture or not, and then later I'm calculating the properties. Okay, so this is usually very expensive, okay, to run it live, but typically I need to know first is I need to calculate flash calculation, also called equilibrium calculation, and then I need to calculate the property estimation. Okay, so one approach that is typically done is that I generate tables, okay, so I can run in two ways. Okay, one of them is live, okay, and then the other one is to pre-compute tables and interpolate on the tables. Later, when you are going to use these properties, you simply come at a given pressure and temperature. Your table will be made in terms of pressure and temperature, and then you're going to be able to calculate all of these. Okay, so this is a bit less expensive, but you still have to run the EOS model. Another approach is to use black oil tables. Okay, and for that I need to generate some black oil parameters. And of course the black oil tables are essentially they can be generated by okay, typically we have now is by an equation of state. I also need to use an equation of state to generate black oil tables. Then I need to use I can also use correlation, or I can use lab experiments. Okay, more or less in that order. Okay, correlations, usually you have to know that your fluid is going to be approximated well by the correlation. You have to test it. And lab experiments, sometimes, it can be used, but is not, because you cannot test all conditions in a lab experiment. So it's a bit limited. So let's talk a bit. The most kind of common approach is this approach of using black oil tables. So we're going to discuss a bit what parameters are used in the black oil tables. So consider here we have at a given pressure and temperature, we have a mixture of oil and gas. Okay, we kind of are going to separate them. They're going to be mixed usually, but we're going to separate them. And what we're going to say is that we're going to calculate the black oil properties. First, we're going to separate both. Okay, we're going to put like a separator at that particular pressure and temperature. Remember, this will be at the bottom of the tubing, will be at the wellhead, will be in the middle of the flow line, whatever you need it. Okay, this is like a mental experiment. So we're going to have our gas, and then we're going to have our oil, and then we're going to pass this separately through the surface process that you have. And remember, what we use, the symbol for the surface process is this guy. Okay, and then we're going to get two products. We can do the same with water, but simply for avoiding, we're going to use only oil and gas. So then we have some gas. This will be local gas and local oil. And here we're going to get some gas that comes, surface gas that comes from gas, and we're going to get some surface oil that comes from oil, from gas. Okay, then we're going to have some surface gas that comes from oil, and we're going to get some surface oil that comes from oil. These are all the products I have. And remember, this P, what is representing could be, for example, could be a multi-stage separation process. Okay, let's say here you have 3 stages, and then you reach the standard conditions, and then you are kind of commingling all the gas, and that's what you get, the gas, and surface oil. Okay, so really the black oil tables, so we have also for all of these properties that are essentially simply the same as the compositional. I simply come for different pressure and temperature and I find out the properties at this particular pressure and temperature. But what is special about the black oil properties is these factors that we are going to define now. And we have seen them before, so it shouldn't be new, but it's this is like the most, before we were looking for only oil or only gas, okay, but now we have two phases. So that's why we have to do this separate. We have to take them to standard conditions, okay? Before, when we had only oil, okay, then we pass it through the standard condition and or only gas. But now we have both, so we have to separate first and then we have to pass it through the surface process. Okay, and we have all of these definitions. So first, the ones that you already know, BO, okay, the oil volume factor is going to be the BO local divided by BO coming from the oil. Okay, the BG gas volume factor is going to be BG local divided by BG standard condition from gas. And then we have this RS that is going to be how much the ratio between the gas that is coming from the oil and the oil that is coming from the oil. So it's going to be this ratio, Bg oil divided by Bo. Okay, and then we have small rs, or also sometimes called Rv. This is the solution. This is the solution gas oil ratio. And this is the solution oil gas ratio. And this one is going to be VO from gas divided by V gas from gas. Okay, and these are all the kind of what we refer to as a black oil model. Okay, you have also some people refer to here as a black oil property, but essentially this is the black oil model. So the behavior of these guys is going to change depending on what kind of fluid I have on my system. Okay, so we are going to try to plot, or let's say if we have an oil, okay, so remember the phase envelope of an oil, it's something like this, right? And if it's an oil, well, I'm going to be operating within this temperature range, just here. So if you see, what we are going to plot here is the VO versus pressure at a fixed temperature. Okay, so typically this one, initially, if you remember, we had this part which has saturation, P saturation, okay, or P bubble point, this guy here. And then from that point, simply I compress, simply it's occupying less volume, and then it's going to go down. And on this side, because it's losing gas, it's always getting lower and lower. Okay, the BG, okay, versus pressure at the fixed temperature is going to be initially very high because you have a low pressure, the gas occupies a lot of space, and then it's going to go down, down, down until you reach the saturation pressure. And at that point, then no more gas exists. So simply I have nothing, there is nothing here because I cannot define at that point. Simply then all the gas will go back into the oil and only I have oil. So then this factor becomes undefined for above that saturation pressure. Okay, then the RS, solution gas oil ratio, big RS, then it's going to be, at some point it's going to be constant, the saturation. Okay, I'm just showing you how it looks like. because at some point, so if I increase above saturation, then I will have simply a single phase, and doesn't matter, I pass it, it's at high pressure or low pressure, simply if I pass the same composition through the same surface process, I'm going to get the same RS. Okay, and then when I go down in pressure, I will start having gas, and that gas will be separated and taken out. Okay, so then I'm flushing, or I'm passing through the surface process an oil which actually has less gas. Okay, so then the RS, the behavior is going to be like that. Okay, and the small RS actually has a similar behavior. And actually, well, not so similar. Actually, it has sometimes something like this. Okay, and then at some point it stops existing. Okay, the behavior of this and it's related to that concept that sometimes you lose a bit of the oil at some particular pressure and temperature, you lose a bit of the oil to the oil phase, and then you kind of the gas will have less or more oil. Okay, but that's how they look like. Now, if you're talking about the composition, which now is a gas, okay, which a gas, remember the critical point is here, and you are working at some temperature, which is here, temperature and pressure. Okay, then what happens is that simply they stop existing. The oil stops existing, but the gas continues to exist. Okay, so for example, BO will be again going up at some point. This is the P of the dew point, but now the BG will continue to exist above the dew point. So then it's going to be something like that. Okay, maybe change a bit of trend, P dew. And the B and the RS, again the same thing. Is going to be going up, and then at some point stops existing anymore, the BU point, and then the RS is the one that is going to be constant. You have this behavior, for example, going up, then you reach, sorry, the dew point is a bit before, and then it's constant, okay? Because at some point, then I will reach, for that temperature, I will reach the dew point, and then here I simply have single phase gas, okay? So it doesn't matter that gas, at what pressure it is, if I flash that gas through the surface process, I'm always going to get the same amount of oil. So how, with these properties, then how do I calculate what we were saying here? We want to essentially having the mass rate of each one of them. Okay, so then I can do I use, for example, one way to do it, computationally very efficient, is, for example, this way. This is from my compendium. So this is a matrix operation that can be computationally can be done like that. You have a vector, which is the standard conditions rate of oil, gas, and water. And then you have the local condition rate of gas, oil, and water. And then here you have a matrix, which is going to make the conversion between these two. And this matrix is simply made up of these black oil properties that we just discussed now. And they are at a given pressure and temperature. So let's say you have a table, then you interpolate, you find these numbers for a given pressure and temperature, and then with this one you could convert from local to standard. But actually what we use most commonly is this one, in which you have the standard and you convert to local. Okay, but this one is simply the inversion of this one, and I believe this one is a bit more difficult to explain than this one. So I suggest we look a bit into this one, and then you trust that when you do the math, then it's inverted into this one. Okay, so you see here that the standard conditions gas is made up of two things. Okay, so you have the gas, the local gas is simply expanding, right? And is ending up on that standard condition gas, okay, is going to be these two. Essentially, it's going to be this one plus this one. Q gas standard condition is the gas from the gas plus the gas from the oil. Okay, and the standard condition oil is going to be these two, that it will be Q oil from oil plus Q oil from the gas. Okay, so that we can take this Okay, so you see that these guys here, this guy times this guy, local gas is going to expand, so that's giving you this term. Okay, and then this oil, first I convert it to surface oil with BO. Okay, and then I multiply by RS to see how much came out of solution. So this is this term. Now we go to standard conditions oil. Okay, this is coming from part of it comes from the oil, which is simply this factor times this oil. Okay, and part of it comes from the gas, local gas. And that local gas, what I do, I take first I expand the gas to standard conditions with BG. Okay, and then I find how much oil that condensed from that gas. So this is going to give you this term here. Okay, so these are, you see very clearly which are the contributions, and then you simply invert that matrix um, and you find this expression. Okay, and that's the expression we will be using later. But you see, it's a bit different if you do it with the black oil model or if you do it with the compositional. Okay, with compositional, simply what I need is simply I need the mass flow, total mass flow. Where is it? Okay, total mass flow, and then I need to have a table which just tells me the fraction of oil and fraction of gas. But when I'm using the black oil model, then I need to create all of these parameters, and then with these parameters is that I make the conversion. But it's very convenient because we are using standard conditions rate, which is very practical, and then we can simply convert directly to local condition. Often, if we are talking about a conventional oil or a heavy oil, so for we can make the assumption that this guy is C equal to 0. Okay, and then this makes the equations here. First, I need to calculate one less parameter, black oil parameter, but then also I have this, so then I can simplify this equation, and this lower part disappears. This part becomes 0, and then the equations become much simpler. Okay, this is not adequate for volatile oil or for gas condensate. So be careful because that contribution, whatever condenses from the gas, then this is important. Also, we have been neglecting here a bit the water. Okay, so water. Okay, we're saying that the water, well, we have exactly the same situation as we have before with the oil and the gas. That we take the water, we take it at the pressure and temperature, we take it through the surface process, and then finally we end up with some surface water, okay, coming from the water. And then we define this factor BW as the volume of the water local divided by the volume of the surface water coming from water. Okay, and this parameter, due to the compressibility, is usually less than 1 because, well, due to the expansion with the pressure, lower pressure, this volume expands. Then typically this guy is much bigger than this guy. But some things that we are a bit neglecting in this approach is that you can also get, so there could be some gas here in solution in the water that you don't see simply since dissolved in the water. And when you go to surface, then it might happen that essentially this becomes, you get also some surface gas that is coming from the water. Usually it's going to be very small compared to the other gas that I have here, okay, this gas and this gas, but it's there. Okay. Another source of water is that in the local gas that I have, I might have also some dissolved water. They can carry a lot of, the gas can carry significant amount of water. Okay, then when I take it to surface, through the surface process, okay, remember that we mentioned the gas comes, volume of the gas from the gas, volume of oil from the gas, but also we can have some surface water from the gas. Okay, and this term also we might be important in some cases. Typically, we have also that could be that the oil, the local oil, also has some water. Okay, so when it ends up here, you will have some water, or that the water will have also some oil, will give you some oil. But these usually the solubilities, they are not relevant, they are not very high, so essentially these can always be neglected. These are like the most important that could be included if they are relevant. Okay, the gas that is in the water and also the water that is in the gas, but we are not including them in this lecture. So I just recommend you to check out my this chapter on my compendium on fluid properties, because there are a few things, a few more details that have to be taken into account. For example, when you want to have a table which will be applicable for variations, for example, of composition.